Hello, welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh. So in this class, we'll try to find the far fields of aperture antennas. So to find out the far fields of aperture antennas, there are basically three steps. The first step is you need to establish the electromagnetic fields on the aperture surface. So you need to find the electric field and magnetic field on the aperture surface, and usually it's known for most of the aperture antennas. Once you have that, you can take the Fourier transform of the aperture fields. That's a step 2. You calculate the two-dimensional Fourier transform of the aperture fields. And the last step, the third step, is you find the far field electric fields from equation 24.1 and equation 24.2. So this equation 24.1 and 2 were already derived in the last class. So once you have the electric field, since we are in the far field, we can always find out the magnetic field simply by taking the cross product of electric field with the radial unit vector divided by eta. So that's the usual way of finding the magnetic field once the electric field is known in the far field. So finding the far fields of aperture antenna is basically three steps. Step 1, 2 and 3. Step 1, you find the aperture fields. Step 2, you take the Fourier transform of the aperture field. Step 3, you find the far fields of the aperture antenna using equation 24.1 and 2. And if you are interested in finding the magnetic field, you just find the cross product of electric field with the radial unit vector and divide by eta. Eta is the wave impedance for the medium. If it is free space, this is around 377 ohm. So now you know how to find the far field of a aperture antenna. So let us try to study some aperture antennas. Start with the simplest one. You consider a rectangular aperture. So this is a rectangular aperture here, and it has dimension Lx into Ly. So this dimension is Lx, this dimension is Ly. So now you want to find the far field of this aperture, which is of rectangular shape, and this portion here is a metal. You have an infinite metal in the xy plane, and you have a aperture which is rectangular in shape in the origin, position at the origin. So dimension is Lx into Ly. And if you assume uniform case means field is uniform inside this aperture. So let us consider that there is a uniform field in this aperture, rectangular aperture, and it is directed along the y-axis. So in that case, your aperture electric field will be simply E0 y hat. So you have a constant electric field which is directed along the y-axis inside this rectangular aperture. Outside this, you don't have any fields. So this is the aperture field. So the first step is already established. So you have a uniform field inside the aperture which is directed along the y-axis. Then the second step is find the 2D Fourier transform of this aperture electric field. So now you can find that. We'll do that in the next following slides. And after that, once you have the 2D Fourier transform of the aperture field, then you can find out the electric field in the far field. FF means far field. Theta component is this, phi component is this. We have already derived this in equation 24.1 and 24.2. So now we just have electric field whose components along the y-axis. So that's why we have only one term here, one term here. Had it been electric field along the x-axis, we'll have one additional term here, additional term here. Had it been some magnetic field existing in the aperture also, then we'll have two more extra term here, two more extra term here. So we just have electric field existing in the aperture which is uniform directed along the y-axis. It will have only, when you take the Fourier transform, it will have only one component along the y direction. This is the Fourier transform. Tilde means Fourier transform. So you need to find the 2D Fourier transform of this aperture field to get the electric field in the far field. Just before that, let us try to see why we have a 2 here, why we are multiplying by a factor of 2 here in the electric field in the far field, theta and phi component. We have already discussed this in one of the previous classes, but I will just revise it again so that you don't forget it. See, you consider free space, infinite free space, you put a PEC surface, it divides free space into two parts. One is right half space, another is left half space. So now what you consider is, you see that there is some sources here. This sources is giving some kind of aperture field here in the aperture here. So in the PEC you have aperture here. Assume that there is some sources in the left half space and it is giving out fields, and that fields at the aperture is known to you. So that's the situation we are considering here. So you know the aperture field, you want to find the fields in the right half space, and aperture is a cutout region in the metal portion. So exactly what we have here. So you have aperture, you know the fields in the aperture, and you want to find the fields here in the right half space. So you use the field equivalence principle to close the aperture, and the effect of the fields which were existing at the aperture can be modeled by an equivalent magnetic current density, which is basically EA cross N. N is a unit normal vector, EA is the aperture electric field. So equivalent magnetic current density would be able to replace this aperture here by equivalent magnetic current density by applying the field equivalence principle too. Then you can find out all the fields in the right half space due to this magnetic current density. So now one more thing is that you can also apply the method of images. So now you have a PEC surface. So now this is a magnetic current density, horizontal magnetic current density above the PEC surface, on the surface of the PEC surface. So you know that horizontal magnetic current density HMD, when you replace this PEC surface, you need to have an image magnetic current density which is in the same direction. So replace this PEC surface. Is very difficult to find the fields using a PEC surface. So you replace it, and the effect of the PEC surface will be taken care of by image current density, which is also along the same direction. So now this is at the surface, at the interface. This is also at the interface. The distance between this gas line and this magnetic current density is 0, but just for illustration purpose I have shown some distance here so that it's clearly visible. So now we have replaced this PEC. Because of this PEC which was existing at this gas line here, you need to introduce a image magnetic current density HMD. They are in the same direction. So now equivalently you have a magnetic current density which is directed along the same direction of same magnitude. Similarly image is also same direction, same magnitude. They are at the same location. You can simply add up. So that's why it will become simply magnetic current density 2EA cross N. This twice factor is coming here. Because of that we have a 2 factor in the electric field, in the far field of the aperture antenna. So now we can find out the 2D Fourier transform of the aperture field. Aperture field is continuous and it is directed along the y-axis. So we'll have only EY component. So EY is E0. So 2D Fourier transform is you multiply by exponential j beta x x dash plus j beta y y dash dx dash dy dash. You integrate it over the whole solution space. But then 2D Fourier transform you do it from minus infinity to plus infinity, minus infinity to plus infinity. But electric field is existing only on the aperture surface, which is from minus Lx by 2 to Lx by 2 and minus Ly by 2 to Ly by 2. So only in this portion electric field is existing, so that infinite integration you have for the Fourier transform will become just finite integration like this. So now look at this expression here. It's very simple to do integration of exponential function. It will become exponential j beta x x dash divided by j beta x. Similarly, this exponential function integration will be exponential j beta y y dash divided by j beta y. Then you can put the limits. You can put the first Lx by 2, then minus Lx by 2, then here also. So finally what you have is this expression for the definite integration of the exponential function going from minus Lx by 2 to plus Lx by 2. Similarly here also. But look at this expression here. We can actually multiply by 2 here and divide by 2 here, then it will become 2j here. Then applying Euler's theorem, this looks like a sine function. So I take out 1 by beta x common, 1 by beta y common. So what expression you have here is sine of beta x Lx by 2 using Euler's theorem. Similarly, this is sine of beta y Ly by 2. So now finally what you have is, since you have divided by 2 here, you should also multiply by 2 in the numerator. It becomes 4e naught. 4e naught sine beta x Lx by 2 beta x. Again you can divide and multiply by Lx by 2 here, Lx by 2 here, Ly by 2, Ly by 2 here. In that case, look at this function. This looks like a sinc function. Sine of x by x is a sinc of x. So you have finally the expression for the Fourier transform of the aperture electric field is simply E0 Lx Ly sinc beta x Lx by 2 sinc beta y Ly by 2. So now what is this beta x and beta y? These are actually components of the beta vector. Wave vector will have x component beta x, y component beta y, z component beta z. So obviously beta x will become beta sine theta cosine of phi, beta y will become beta sine theta sine of phi, beta z will become beta cos theta. This is a projection of beta vector along x-axis, y-axis and z-axis, beta x, beta y, beta z. So if you have forgotten what is a sinc function, this is how a sinc function looks like. Sinc function is maximum and when x is equal to 0. This is sinc of x with respect to x. At x is equal to 0, sinc function has the maximum value, then amplitude keeps on decreasing with higher values of x. It's very symmetric. Along the negative x-axis also you have the same curve. So you have the expression for the electric field and electric field. You can find out now what is the E-plane electric field. See, basically your electric field in the aperture was directed along the y-axis, so you will have maximum electric field for the radiation of the aperture antenna along the y direction. So the plane in which you have the maximum electric field is called the E-plane. So E-plane for this antenna will be along YZ plane. YZ plane means phi should be equal to pi by 2. So you have the expression for 2D Fourier transform of the aperture electric field. Here you need to apply the condition for E-plane where phi is equal to pi by 2. You have the expression beta x, beta y, beta z. Beta z is not existing here because aperture field is confined in xy plane. So beta x when phi is equal to pi by 2 will become 0, beta y will become simply beta sine theta. So put that in the expression for the Fourier transform of the aperture electric field. What you get is this will become 1 because sinc function you have just seen now has a value of 1 when this argument is equal to 0. Then you have sinc of beta y Ly by 2 and this will become sinc of beta y is beta sine theta Ly by 2. So you can write down the far field expression of the electric field of the aperture antenna, which is uniform rectangular aperture, for the E-plane simply turns out to be like this. And when you put the phi is equal to pi by 2 for the E-plane, the far field phi component will become 0 because cos of phi is equal to pi by 2 is 0. Sine of phi pi by 2 is 1. That's why you have the expression electric field in the far field of the uniform rectangular aperture in the E-plane will have only theta component. It will have 0 phi component. Similarly, you can also find the H-plane. H-plane is perpendicular to the E-plane, so it will be in the XZ plane. In the XZ plane, phi is equal to 0. You put that condition in phi is equal to 0. Beta x will become beta sine theta, beta y become zeros. Then your expression for the EAY will become simply now E0 Lx Ly sinc of beta sine theta Lx by 2. Similarly, you can find out the electric field in the far field of the uniform aperture, rectangular aperture. Theta component will become 0 now because phi is 0, sine of phi is 0, cos of phi is 1. So you will have the phi component. So in the H plane we have only phi component. In the E plane we have only theta component. So now you are also interested in finding the nulls of the radiation pattern. You can find out. So what is the electric field in the E plane will have only theta component. This was the expression for the electric field in the far field of a uniform rectangular aperture. Null will occur when this sinc function is equal to 0. This sinc function is equal to 0 when beta Ly by 2 sine theta n is equal to n pi. Sinc function will 0 when this argument is equal to n pi. So you can simplify it. Sine theta n will become n pi divided by beta Ly by 2. So finally you simplify, beta is 2 pi by lambda. So sine theta n will become n lambda by Ly. So now this will give you the nulls of the radiation pattern of the E plane of the uniform rectangular aperture. So if you want to find the beam width between the first two nulls for the E plane, that will be when n is equal to 1. So 2 sine inverse lambda by Ly. This will give you the beam width between the first two nulls for the E plane radiation pattern of the uniform rectangular aperture in radians. So if you want to convert into degrees, then this will become 114.59 sine inverse lambda by Ly in degrees. So this is the beam width between first two null for the E plane radiation pattern. Similarly, you can also find out beam width between first two nulls for H plane. In that case, it will become 114.59 sine inverse lambda by Lx degrees. So this was lambda by Ly. This will become lambda by Lx. For the E plane, this will be lambda by Ly. For the H plane, it will be lambda by Lx. So what you can observe is that beam width between first two nulls will be dependent on the dimension of the aperture of the rectangular uniform aperture antenna. You can also find out the half power beam width. For the power, you have to see, this is the electric field. For the power, you have to square this term, divide it by eta. In that case, you will have a sinc square term here, sinc square beta sine theta Ly by 2. So half power means sinc square beta sine theta Ly by 2 become halves. All other terms are almost constant, no? So sinc square beta sine theta Ly by 2 will become half. In that case, beta sine theta Ly by 2 will become 1.391. So you can find out what is sine theta now. 1.391 lambda by pi Ly. What is 1 by so sine theta will become 1.39 lambda by pi Ly. So now you divide this 1.39 by pi, you get 0.443 lambda by Ly. So you can find out half power beam width for the E plane would be 2 sine inverse 0.443 lambda divided by Ly in radian. If you want to convert into degrees, it will become 114.59 sine inverse 0.443 lambda by Ly. So the half power beam width for E plane is dependent on the Ly, and you can observe that beam width between the first two null is smaller than the half power beam width, because you see here you have 114.59, but here you have same 114.59, but then you see the argument here is lambda by Ly, but the argument here is 0.443 lambda by Ly. So this value will be smaller. Similarly, you can also find out half power beam width for H plane. That would be 114.59 sine inverse 0.443 lambda. Instead of Ly, it will become Lx degrees. You can find out. So what you can observe is the half power beam width or beam width between the first two nulls are inversely proportional to the length in the corresponding cutting plane. If you increase the length, half power beam width will decrease, and as well as the beam width between first two nulls will become smaller and smaller. So the question is, how do you calculate the directivity for such kind of aperture antennas? There is a simple formula here. You can apply the conventional formula for finding the directivity for aperture antenna using the conventional formula, and you can simplify it by that derivation is given in the Stutzman and TLA books, which is one of the references for this course. You start with the conventional definition of directivity and you can simplify it, and finally the directivity for aperture antenna is simply 4 pi by lambda square integration, double integration over the aperture of the aperture electric field, square of that divided by square of the aperture electric field integration over the aperture area. So now here in this case we can find out that we already know that uniform rectangular aperture, so the field was directed along the y-axis and it has uniform value E naught. E naught was the field which is directed along the y-axis. So now this will become simply E naught here. Here you have a E naught multiplied with the area surface element, small surface element integrated over the area. So what you are doing is, since E naught is constant, you multiply with the area and square of that. Here what you are doing is E naught square into area. So now you will have area square here, you will have only area here. So area and area square cancels out, you just simply have area here. So what you will simply get is 4 pi by lambda square aperture area. So what is the aperture area? It's a rectangle and it has length and width as Lx and Ly. Area will be simply Lx Ly. So this is a very simple expression for finding the directivity of uniform rectangular aperture. Simply find 4 pi lambda square Lx into Ly. Lx and Ly are the dimension of the uniform rectangular aperture. One more observation is that since it's a sinc function, see in the electric field expression you have an expression for sinc function. So obviously the radiation pattern will have a behavior of the sinc function, and as you know that sinc function, the side lobe level is approximately minus 13.2 dB. So this kind of radiation pattern will also have side lobe level. First side lobe level will be around minus 13.26 dB. We'll derive this in the next slide. So we are having sinc function in the radiation pattern of the electric field in the far field. We want to find the maxima for that. So when you want to find the maxima of a function, you differentiate it in equate it to 0. Sinc function is sin x by x. You differentiate it, then equate it to 0. The first maxima will be at x equal to 0. And you already seen the sinc function plot, and it has maximum at x equal to 0. So now that is for the main beam. For the second maxima, that is the first side lobe, you can find out the value for x. X turns out to be 4.5. In that case, the value of the second maxima sinc function sin x by x, sine of 4.5 by 4.5, this will turn out to be 0.217. So this turns out to be 0.217. In that case, you find it in dB. 20 log of 0.217 is minus 13.26 dB. So this is the level of the side lobe level. So all other side lobes will have lower value than this. First side lobe will have side lobe level of minus 13.26 dB. So that's characteristics of the radiation pattern of uniform rectangular aperture in the far field. It will have a side lobe level of minus 13.26 dB. So this is the plot of the radiation pattern of a uniform rectangular aperture. The dimension is 5 lambda and 5 lambda. That's why we have 5 lambda here, minus 5 lambda here, 5 lambda here, minus 5 lambda here. So what is the x-axis? X-axis is this, beta Ly sin theta sin phi divided by 2 pi. This is the y-axis, this is the x-axis. X-axis is beta Lx sin theta cos phi divided by 2 pi. Theta and phi, theta will vary from 0 to pi by 2, or let's say 0 to pi, or phi will vary from 0 to 2 pi. So if you keep on varying the value of theta and phi, you will see that the range of value you have for this beta Lx sin theta cos phi divided by 2 pi will be in between Lx by lambda, from minus Lx by, this would be minus Lx here, minus Lx by lambda to Lx by lambda. And this y-axis beta Ly sin theta sin phi divided by 2 pi will have range of value from minus Ly by lambda, that should be minus here, minus Ly by lambda to Ly by lambda. So this is range of value for the x-axis and y-axis. That's what we are seeing here. And this plot, you can see that it has a maximum value at theta is equal to 0, this radiation pattern, and it's almost like a sinc function. You have many side lobes here. The first side lobe, what is the level? Level was minus 13.26 dB down. All other side lobes are smaller than the first side lobe. And this looks like a sinc function in 3D case. And this area is a ellipse, and that would be 1 by Lx square beta Lx sin theta cos phi 2 pi whole square plus 1 by Ly square beta Ly sin theta sin pi divided by 2 pi whole square less than or equal to 1 by lambda square. This is the equation of the ellipse for this area here. So you have a main lobe, you have a first side lobe which is minus 13.26 dB down. You have many more side lobes which are of lesser amplitude than the first side lobe. So this is the typical radiation pattern of a uniform rectangular aperture antenna. So we have discussed about the uniform rectangular aperture antenna. Let us try to analyze the field radiated from a uniform circular aperture here. Assume that this is a uniform circular aperture. We are considering its position in the xy plane, and the radius is a, and its position at the origin. We have an infinite conducting plane in the xy plane, and at the origin we have a uniform circular aperture of radius a. So we want to find the field radiated from this uniform circular aperture here. Assume that there is uniform electric field which is directed along the y-axis. Aperture field is E0 y hat for radius less than or equal to a. A is the radius. So we have uniform aperture field here directed along the y-axis. So we have established the field inside the aperture, the first step. Then second step is to find the 2D Fourier transform of the aperture field. This is the expression you have for the 2D Fourier transform. As you can see that this expression for the 2D Fourier transform is in the xy coordinate system. So but then this aperture is circular in shape. You need to change the coordinate system now so that you can do proper derivation for the 2D Fourier transform for the uniform circular aperture. We can just change it to spherical coordinate system. X dash will become simply r dash sin theta dash cos phi dash. Y dash will become r dash sin theta dash sin phi dash. This dash or prime coordinates for the source. That's why we put a dash here, or prime coordinates for the source. Since the aperture is in the xy plane, what happens to theta dash? Theta dash is pi by 2 in the xy plane. Hence x dash will become r dash cos phi dash, y dash will become r dash sin phi dash. And we also know that beta x is beta sin theta cos phi, beta y is beta sin theta sin phi. This is a projection of the beta vector in the xy axis. So now beta x, x dash, beta y, y dash will simply become beta r dash sin theta cos phi dash plus beta r dash sin theta sin phi dash. So now if you take out beta r dash sin theta common, what you have here is cos of phi minus phi dash. So this term in the exponential for the 2D Fourier transform can be replaced by these polar coordinates. So you also know that in the xy plane, in the polar coordinate, dx dash dy dash will become r dash dr dash d phi dash. So the Fourier transform, 2D Fourier transform in the polar coordinate will become r is going from 0 to a, phi is going from 0 to 2 pi, and this is the aperture field, and the exponential term will simply become now exponential j beta r dash sin theta cos phi minus phi dash. So now you have the 2D Fourier transform in the polar coordinates. And also assume that there is no field variation along the phi, because your field was uniform. It was directed along the y-axis and it was constant, E0. In that case, your aperture field will be dependent only on r, it will not depend on phi because of the circular symmetry. So in that case, you can separate out this double integration. So this integration here, which is dependent on the phi, you can do it first. Then you can do the integration over r dash later on. You do the integration over phi dash first, then do the integration over r dash. But looking at this term, this looks like a Bessel's function. So the inner integration looks like a Bessel's integral, and it gives you 2 pi times Bessel's function of first kind of 0 order. So replacing the inner integration by 2 pi times Bessel's function of first kind of 0 order, argument is beta r dash sin theta. So the expression you have for the 2D Fourier transform for the aperture field is simply 0 to a 2 pi j0 beta r dash sin theta. This is the aperture field. In our case, it will become E0 r dash dr dash. Just remember that J naught was like a cosine function. See, we have studied about the Bessel's function of first kind in one of the classes when we try to find the cylindrical waves. So J naught is like a cosine function, so the value of J naught at argument equal to 0 would be 1, and after that it will have oscillation, lot of oscillations, and zero crossings for the cosine function is always fixed. Distance between the zero crossings in the cosine function is always constant, but for the Bessel's function it was irregular, it was changing, it was not fixed. And you can also observe that the amplitude was not constant. For the cosine function, amplitude is always constant, peak amplitude is always constant, but for the Bessel's function, peak amplitude was decaying. There was a amplitude taper, so you will have irregular roots and amplitude taper. So J0 is like a cosine function with irregular roots and amplitude taper. You can further simplify this expression. Now EA RDS will become simply E0, so you can take out E0 is a constant, you can take it outside, and you also have another Bessel's identity. When I integrate x J0x dx, I will get x J1x. And also remember that we have also discussed about this Bessel's function of first kind of first order was like a sine function. That means when argument is 0, it will become 0. Sine function, sine of 0 is 0. And it will also have irregular roots and amplitude taper. So now let us make a substitution. Beta RDS sin theta is equal to this symbol here. Then d of this symbol will become beta sin theta RDS. So you substitute that in the expression and you do the integration. What you will get is beta a sin theta J1 beta a sin theta divided by beta sin theta squared 2 pi E0 is the final answer you have for the aperture electric field 2D Fourier transform. Can cancel out this beta sin theta here, then finally 2D Fourier transform of the aperture electric field will become 2 pi E0 a J1 beta a sin theta by beta sin theta. So now you have the 2D Fourier transform of the aperture fields. First step is done, second step is also done. What is the third step? You find out the far field of the aperture antenna by using equation 24.1 and equation 24.2. And you also have a factor 2 here by application of the field equivalence principle to a method of images. So you can find out the electric field in the far field. It will be 2 j beta exponential minus j beta r by 4 pi r, and since we have only y component of the electric field, we don't have any magnetic field. X component of the magnetic field is not existing, so you will have only one term here. Similarly, you will also have only one term here. This is the electric field in the far field, theta component, electric field in the far field, phi component. You can plug in the value of this EAY here. You will get the electric field in the far field of the aperture antenna. So this is the final expression you have for the electric field in the far field of the uniform rectangular aperture. And it's not rectangular, it's uniform circular aperture antenna. You can also find out the directivity. That's the formula you have for the aperture antenna. That's 4 pi by lambda square. EA ds integrate over double integration over the aperture area, square of that divided by EA square ds integration over the double integration over the aperture area. Now aperture is having electric field E0, which is constant here, is also constant here. Simply what you have is E0 square area square here and E0 square area here. So simply your directivity will become 4 pi lambda square area of the circle pi a square. So directivity is 4 pi square a square by lambda square. This is the directivity of the uniform circular aperture. We are also interested in the 3 dB pattern point as well as half power beamwidth, like last time we have done for the uniform rectangular aperture. So 3 dB point we will find out for the E plane and H plane. E plane is where you have the maximum electric field. Since your aperture field was directed along the y-axis, we will have maximum electric field along the y-axis. So the aperture, the E plane would be, for this aperture antenna, would be YZ plane, where phi is equal to pi by 2. You put that phi is equal to pi by 2, electric field will have only theta component, phi component will become 0. And you want to find the 3 dB point, half power point. In that case, this term here, this argument here, beta A sin theta should be equal to 1.6162. Amplitude will become half 1 by root 2, or the power will become 1 by half when this beta A sin theta 1 is equal to 1.6162. So you can find out sin theta 1. Sin theta 1 turns out to be 0.5145 lambda by d. D is the diameter of the uniform circular aperture. So you can find out half power beamwidth now. For the E plane is 2 sin inverse 0.5145 lambda by d radian. You can convert into degrees, then it becomes 114.59 sin inverse 0.5145 lambda by d degrees. So d is the diameter. So if you keep on increasing the diameter, half power beamwidth will become smaller and smaller. You can also find out the beamwidth between the first two nulls, or beamwidth between first two null for the first 0 or null point. So first 0 will be when beta A sin theta is equal to 0. Beta A sin theta null is equal to 3.8317. So when this term becomes 3.81317, you will see that this Bessel's function of first order and first kind will have a null. First null is, for the Bessel's function of first order and first kind will have a null when this argument beta A sin theta is equal to 3.8317. This is the first null for that. From there you can find out beamwidth between the first two null for E plane, that will be twice of sin inverse 1.2197 lambda by d. D is the diameter of the uniform circular aperture. In radian you can find out, if you want to find in degrees, it will become 114.592 sin inverse 1.2197 lambda by d degrees. So if you keep on increasing the diameter of the uniform aperture, the beamwidth between first two null become narrower and narrower. So this is the typical radiation pattern of the uniform circular aperture of radius A is equal to 5 lambda. Like last time, this x-axis is beta A sin theta cos phi divided by 2 pi, and y-axis is beta A sin theta sin phi by 2 pi. And you can see that the beam has a maximum at theta is equal to 0, that is the main beam, and there are many side lobes. The first side lobe was around minus 13.62 dB, then you will have a smaller side lobes. And this is a typical radiation pattern of a uniform circular aperture antenna. That's all for this class. Thanks for your attention.